All right, boys and girls, we're going to start in with a little background on our new unit, talking about waves. What are waves and what are those properties of waves? So I'll follow along on our read aloud here. Starting with, what is a wave? When you're relaxing on an air mattress in a pool and someone does a cannonball dive off the diving board, you suddenly find yourself bobbing up and down. You can make something move by giving it a push or pull, but the person jumping didn't touch your air mattress. How did the energy from the dive travel through the water and move your air mattress? The up and down motion was caused by the peaks and valleys of the ripples that moved from where the splash occurred. These peaks and valleys make up water waves. Waves carry energy. Waves are rhythmic disturbances that carry energy without carrying matter, as shown in figure 1a. You can see the energy of the wave from a speedboat traveling outward, but the water only moves up and down. If you've ever felt a clap of thunder, you know that sound waves can carry large amounts of energy. You also transfer energy when you throw something to a friend, as in figure 1b below. However, there's a difference between a moving ball and a wave. A ball is made up of matter, so when it's thrown, the matter moves from one place to another. So unlike the wave, throwing a ball involves the transport of matter as well as energy. And see here, it says the waves created by a boat move mostly up and down, but the energy travels outward from the boat. You can say when the ball is thrown, the ball carries energy as it moves. There we go. All right, so looking at this little image here, you can say as the students pass the ball, the students' positions don't change. Only the position of the ball changes. So here, right, they're passing the ball from one person to the next to the next. They're staying in the same place, but the energy, that ball is moving along that line of students. And just like here too, in a water wave, those molecules bump each other and then they pass the energy from one molecule to the next as it goes through that matter. All right, a model for waves. How does a wave carry energy without transporting matter? Imagine a line of people as we showed above. The first person passes to the second, who passes to the next, and so on. Passing a ball down a line of people is a model for how waves can transport energy without transporting matter. Even though the ball has traveled, the people in the line have not moved. In this model, you can think of the ball as representing energy. What do the people in the line represent? Think about the ripples on the surface of a pond. The energy carried by the ripples travels through the water. The water is made up of water molecules. It is the individual molecules of water that pass the wave energy, just as the people in figure 2a pass the ball. The water molecules transport the energy in a water wave by colliding with molecules around them, and that's what you saw in this part over here. Mechanical waves. In the wave model, the ball could not be transferred if the line of people didn't exist. The energy of a water wave could not be transferred if no water molecules existed. These types of waves, which need to use matter to transfer energy, are called mechanical waves. The matter through which a mechanical wave travels is called a medium. For ripples on a pond, the medium is the water. A mechanical wave travels as energy is transferred from particle to particle in the medium. For example, a sound wave is a mechanical wave that can travel through air, as well as solids, liquids, or other gases. The sound wave travels through air by transferring energy from gas molecule to gas molecule. Without a medium such as air, you would not hear sounds. In outer space, sound waves can't travel because there is no air. Here's the model of a transverse wave. All right. In a mechanical transverse wave, The wave energy causes the matter in the medium to move up and down or back and forth at right angles to the direction the wave travels. You can make a model of a transverse wave. Stretch a long rope out on the ground. Hold one end in your hand. Now shake the other hand back and forth. By adjusting the way you shake the rope, you can create a wave that seems to slide along the rope. When you first started shaking the rope, it might have appeared that the rope itself was moving away from you, but it's only the wave that was moving away from your hand. The wave energy moves through the rope, but the matter in the rope doesn't travel. You can see that the wave has peaks and valleys at regular intervals, as shown in Figure 3. The high points of a transverse wave are called crests. The low points are called troughs. You can see those labeled here. As that wave goes, as it gets up to its peak, there's the crest, and then when it goes down to its valley, there's the trough down here. And that just kind of keeps on continuing right along. So crest and trough are some important words that we'll need to know for being able to label the parts of a wave here. All right. A compressional wave can travel through a coiled spring toy like a slinky. As the wave motion begins, the coils near the string are close together, and then the other coils are far apart. And you can see that here. They're really compact together, a little bit more space right here. And they tied a string on here so you could see where that travels. The wave seen in the squeezed and stretched coils travels along. So when you send that energy along, that energy travels, and now it's right here. And eventually it passes through that string, and now you can see that energy is over here now. Okay. Compressional waves. Mechanical waves can be either transverse or compressional. In a compressional wave, matter in the medium moves forward and backward in the same direction the wave travels. You can make a compressional wave by squeezing together and releasing several coils of a coiled spring toy. You see that the coils move only as the wave passes, then they return to their original position. So like transverse waves, compressional waves carry only energy forward along the spring. In this example, the spring is the medium the wave moves through, but the spring does not move along with the wave. All right, sound waves. When you talk or sing, sound waves are compressional waves. If you hold your finger against your throat while you hum, you can feel vibrations. That's your vocal cords vibrating. If you touch a stereo speaker while it's playing, you can feel that vibrating too. All waves are produced by something that is vibrating. All right, so vibrating sounds. Look at the drum. When you hit the drum head, it starts to vibrate up and down. As the drum head moves upward, the molecules next to it are pushed closer together. This group of molecules that are closer together is a compression. As the compression forms, it moves away from the drum head, just as the squeezed coils are moved along the coil in the spring toy. When the drum head moves downward, the molecules near it have more room and can spread farther apart. This group of molecules are farther apart. It's called a rarefaction. A rarefaction also moves away from the drum head. As the drum head vibrates up and down, it forms a series of compressions and rarefactions that move away and spread out in all directions. And that's what makes the sound waves. We're going to skip the electromagnetic right now.